things that's a little bit different about the structured mesh discretizations and frameworks that I'm going to talk about is it's not something that you just, quote, call. When you want to solve a linear system, you want to do a matrix inversion, you can think about just calling a very specific operation. We've gone through, in trying to define what I'm going to talk about, is this software a library? Is it a framework? What does this all mean? So this talk is not a how-to guide so much as to how to use a specific set of software. It's really a step back, think about what you're doing. What are the choices that you make? What are the design decisions that you make when you decide about using a specific piece of software? Okay, so this is the outline. I want to step back, and again, we're talking mostly about PDEs, time-dependent PDEs, although you can use it for time-independent. Choosing your spatial discretization. Why do we keep talking about mesh refinement? What are the pros and cons of structured versus unstructured? And I'll give you a heads up, I'm biased towards structured, so I'm going to give you more pros of structured. The talk following this is about unstructured meshes, and so I'm going to let them tell you the pros of the unstructured mesh. AMR, adaptive mesh refinement, that phrase applies for structured mesh and unstructured. I'll focus on structured mesh. What is AMRX? That's the name of the software package. It's rapidly transitioning to being AMRX. We've thought about a logo with a dinosaur, but we feel like that kind of sends the wrong message. So if anybody has great logo ideas, we're still taking them. We've realized we really, really need a logo. It shouldn't be a dinosaur. Okay, what does AMRX do for you? What doesn't it do for you? A very high level, how do you use it? What do you need to have existing or want to do in order to make use of it? And then we do have some hands-on exercises that the point of which is basically to show you that it's a pretty easy piece of software to get started with, give you a very bare bones introduction to it, and then I'd be very happy to talk to anybody who thinks it might be useful for them. I will point out that in the room there are actually 2 existing collaborators who are using this software, and one who we almost got to use it. But somebody else hired him, and I can't tell where he is. But okay, so we want to solve a time-dependent PDE. So Mark gave a great introduction to what's the first thing you have to do. You have to know what your equation is. You write the equation with partial derivatives and things. To put it on the computer, you have to discretize it. Okay, so let's take the very simplest case. It's a system or a single PDE or a system of PDEs. You want to solve it. You have a regular domain. Easiest thing in the world. If you have unlimited resources, this is what you do. You put down a regular mesh, a uniform structured mesh. You use some discretization, some FCTS or some implicit scheme that marches forward in time. You have a fixed time step. You just solve the thing. Okay? There's an example. U new equals U old plus speed times dt. That's some advection example. End of story. IJ are each little thing. Now, you might want to run a big enough system that it doesn't fit on a single core or a single node. So you've got to parallelize it. Easiest way in the world to parallelize it, you say, I'm going to break this domain into chunks. It's called domain decomposition. I'm going to put each chunk on a different process or a different node. And you can see there's boxes getting distributed to cores. Use domain decomposition. You probably use MPI to do some exchange of information. End of story, you are done. Okay, in a world of unlimited resources and simple problems, this is what you do. So that would be great. I think Laurie gave a great introduction to why we don't actually do that. Because gone are the days where that's what we want to solve. That one's been done. Most problems you want to solve aren't that simple. This is an example of a flame. A lot of processes. You've got advection, diffusion, combustion, reactions going on. Then you have a lot of nonlinearities in how you can compute the transport coefficients. They depend on the solution. A lot of things going on. We use the words starting with multi a lot. So multi-physics means there's more than one thing going on. There's species being advected, there's species being diffused, there's species being reacted. Here I'm talking about chemical species. In astrophysics, it could be nuclear. Multi-rate, that typically means multiple time scales. Some things move at an advection velocity, they move with the fluid. Some things move at an acoustic time scale. There are reaction time scales, all sorts of time scales in the problem. And it turns out that in many cases, you don't want to solve them all with the same time step. So multi-rate means now you've got to discretize different processes with some sort of different operation. You're going to hear a lot more about that from Carol this afternoon. Multi-scale typically means multiple spatial scales. So again, certain things have much finer spatial scaling inherent in the problem. Regardless of how you discretize it, the physical problem scale is different. And then, of course, as Laurie also introduced, we don't often solve flow in a box. I would love to solve flow. I would love to solve flow in a box. It would save me a lot of headache. But That's not the world where we operate. So you have complex domain boundaries. On the example there, that's a chemical looping reactor. That's for one of our multi-phase problems. And the flow is entirely in the areas that are colored. So you've got a lot of empty space if you put that geometry into a box and discretize it. So you've got to have some way of zooming in on that. That's a complex geometry. You also have sometimes complex material boundaries, where you might want to treat two parts of the flow differently, even though it's not a wall. And so you might want to do something different on each side of that. And as you've learned on Cooley today, you don't have unlimited resources. Somebody had to apply for that computer time. Somebody's telling you how much you can use. You also may want to finish this problem in your lifetime. So you're looking for every... Sorry. Yes, in the real world, this is the way we think. I have a certain attention span. I want my problem to finish running before I forget what it was. And as Laurie also pointed out, I probably don't want to do one hero calculation anymore. It used to be in computational science that you could spend 2 years setting up this problem and running it, and you had a single hero calculation, and you could mine that for papers, and wow, you were a hero, and it was a hero, and life was good. And now somebody's going to say, well, can you replicate that? And what happens if you change this? And can you do an ensemble? So we have to be able to run these things in a finite amount of time, where finite is, again, your attention span in some sense. So long story short, you need some kind of adaptivity. That's sort of the takeaway from this is, even if you think you're doing a really simple problem, once you solve the simple problem, you're going to want to make it harder because that's where the interesting stuff happens. So you need some kind of adaptivity. And again, it can be adaptivity that's fixed in time because it comes from the geometry. It can be adaptivity that changes with the solution because, again, if we're doing time-dependent PDEs, they're probably changing in time. OK, so again, my focus is on structured mesh refinement. You're going to have a whole talk on unstructured. And so, again, everything is in the context here of structured. So if you want to stick with structured meshes, and I'll tell you in a little bit why I think they are a good idea, how can you refine? Now, unstructured meshes, as I think you've seen from the pictures, obviously have the ability to refine, right? You fix your grid cells based on the solution, the geometry, et cetera. In some sense, you have many more degrees of freedom in constructing your mesh because it doesn't have this constraint of regularity. In structured meshes, what are the ways to adapt? And different ways, there's sort of three primary ways. One is, I'll use the phrase very broadly, mapped meshes. Now here's an example of a very simple mapped multi-block. Laurie mentioned this. Multi-block means you have multiple, in some sense, subdomains within a problem, and each subdomain is regular. And they have some interface that can or cannot be that regular. Again, what you know is that cell I plus 1, comma j, comma k, is next to cell I, comma j, comma k. So that's what you get from being regular. You know your connectivity. Here you have metric terms, though, right? It's not, it's what we call logically, each submesh here is logically rectangular. So logically rectangular means I plus 1 is next to I. The fact that it's logically, not physically, means yes, it's actually curved. So that's one way to refine. So you actually can do, they call it body-fitted meshes sometime. You'll hear the phrase terrain-following meshes in atmospheric modeling. Now, if you want to keep more regularity and not be fitting the meshes to your geometry, you might consider some sort of what we call block-structured or point-wise refinement. The middle case is one that is kind of our classic picture of block-structured refinement. You have patches at different resolution. I'll talk more about this in a minute. There are different refinement strategies. This one is called patch-based. There's another form that's called octree or quadtree-based, quadtree in 2D. Those are subsets of the same general type. Point-wise refinement, I didn't put a picture of. It's something that was very popular early on for reasons having to do with things like vectorization. Point-wise refinement is kind of on the way out, so I'm not going to say a lot more about that. OK, pros and cons. Let's assume that your goal is to actually solve a problem numerically. So you want to get to the point where you can study whatever that physical process is. You want to understand how it changes with resolution, all of these things. You may or may not want to spend a lot of time thinking about the discretization. So one comment is, in the structured grid world, it is easier to discretize the operators that you know. The gradient in the x direction is orthogonal to the gradient in the y direction. That's a really convenient fact. Connectivity we talked about. You know if you're taking the gradient in the x direction, then you difference in the x direction. We know what the x direction means. The I index aligns with the x direction. There are a lot of simplifications that you could make. So if you're somebody writing this for the first time, this is an easier way to go. Another thing that people don't think about as much in structured grid, if you grow up in structured grid land, you take it for granted, is a lot of your operators, you get an extra order because things cancel. If you take a Laplacian is a gradient minus a gradient. Those discretizations, if they're uniform and dx is constant, you get an extra order because of cancellation. So that's really convenient. There's a lot of convenience in this. Okay, now when you look at architectures, if anybody runs on the KNL machines, for example, the Cori 2 machine at NERSC, vectorization is everything. So if you can't vectorize your loops, they're going to run a whole lot slower than your scalar loops. So you really want to be able to put things in an order to lay out your data and to write your operations in such a way that you can vectorize. Again, the structured nature, it just makes it easier. I'm not saying you can't do it in unstructured, I'm saying it's easier in structured. You have contiguous blocks of data, it's a more natural thing to do. So stepping now off core and off node, you need some kind of hybrid parallelism. The reason you want hybrid is in some sense, MPI is great. I love MPI, it's a great way. We typically do domain decomposition by distributing grids to processes. If you have too many MPI ranks, you start to see some slowdown. So there's a sweet spot. There's a sweet spot where you have MPI balanced with something. The something right now tends to be OpenMP. At some point, if people want to talk programming models, we can talk about other strategies. But for now, let's talk MPI plus OpenMP. It's a very natural thing to distribute grids to processes and then to use OpenMP to thread over tiles within a grid. I'm going to say the word tiles or logical tiling. Again, we can come back to that if people are interested. OK, so I've dodged the whole geometry question. I said, oh, it's great. You have I plus 1. It's really regular. Now you want to do geometry. And you have to have some way of addressing that if you're going to use structured mesh to do complicated problems. So the sales pitch for structured grid tells you two things. One is, if you do an unstructured mesh, your mesh everywhere adapts to the fact that you have irregularity at the boundary. If you use a structured mesh discretization, the irregularity can be localized near the boundary. It's a design choice. Okay? Some things are easier, some things are harder. So in the two airplane pictures, gratuitously pulled off the internet, and I apologize, I forgot where I got them. On the left is a structured grid with an airplane in the middle, and what you can see is there's refinement near the airplane, but there's also, and it's very hard to see here, there are these cut cells. It's an embedded boundary approach, cut cell. Some people call it immersed boundary. It's I think, embedded boundary or cut cell are the best things. You're taking rectangular cells and you're literally cutting them with a planar representation of the geometry in that cell. And if you have very small cells, a planar representation is pretty good. And so what happens here is the mesh is distorted, or it's cut in the cells adjacent to the airplane. But away from that, it's completely regular. So if the boundary is a very small part of your domain, you might say, you know what, I'll concentrate, I'll spend a little extra work there, and I don't have to change what I'm doing everywhere else. On the right, obviously, is an airplane in an unstructured mesh, and you can see that the entire mesh is adapted to the presence of the airplane. The other thing that is relevant, and I'll let the unstructured mesh people talk about this, is mesh generation. If you've got a moving airplane in your domain, the mesh will have to adapt to where the airplane is at every time. The mesh generation in the structured case is basically you're literally cutting, you're intersecting a solid airplane with a structured mesh. It's a much faster process. Not that it's trivial, but in both cases there is software to do it. Take it to the bank. You don't want to write either of them. You want to use a package for both of them. Conceptually, one simpler than the other. When you use the packages, maybe it's all taken care of. That's an interesting question. Okay, just to be fair, structured grid is not perfect, and I told Mark ahead of time that it's up to him to what's the phrase, blow the horn? Blow the horn for unstructured mesh. So the con, of course, of the structured mesh is at these physical boundaries, now you've got cut cells, and now you've got to think about what a cut cell algorithm looks like, and there's research going back 20 or 30 years on how to do that effectively, and there's still research going on about the best way to do that. So it's not that easily a solved problem. You also, because you're used to working in the world of structured meshes, you have algorithms that may depend on that cancellation. Now all of a sudden you're losing order. You're losing order of accuracy at the boundaries, and that costs you. You've got to do special things there. So now you've got to think about how you want to deal with that. You've got to do special stuff. You're doing it at a smaller number of points, but that may or may not parallelize as easily because those points are now distributed across your domain. The other thing about once you have an unstructured mesh, you've written a general discretization. You don't have to be doing special things, so you can modify the resolution of the unstructured mesh without creating a coarse-fine boundary. Now, they do also have AMR in unstructured. Again, I'll leave that for the next talk. Okay, so block-structured AMR. What do I mean by this? In block-structured AMR, the solution is defined on a hierarchy of levels of resolution. So when I talk about level, it really corresponds to the DX, right? Typically, we refine by a factor of 2 or 4. There are some codes that refine a factor of 3 because they keep cell centers in the same place. In this case, every level is a union of rectangles. The rectangles do not overlap, although there are codes with overlapping, but in this case, we'll have a union of non-overlapping grids or patches. It's adaptive. That means the patches can change dynamically. If you know about some of the software that's out there, you'll hear about octree refinement codes like Flash, AMR Claw. There's a number of packages that use this quadtree or octree refinement. Basically, what happens there is if you want to refine any one point in an existing mesh or existing patch, you refine the entire thing. This gives you very nice information about connectivity between levels. I will give you my personal opinion. If you're doing a very simple problem where you don't have a lot of flops, you don't have a lot of computational work, you spend a lot of time worrying about that connectivity because that's where you see the time. Once you go to more serious multiphysics problems, that's the least of your problems. So there are people who disagree with me. That is my perspective. It turns out that you can do octree refinement in the context of a patch-based code. In fact, one of the things that's happening with AMRX is there's a code out there called Flash. It had support from a package called Paramesh. Paramesh is no longer being supported, so Flash is actually inserting an AMRX layer as an infrastructure. We're taking the patch-based AMR, doing some specializations. So people think of these as really different. They're actually, I would say the octree is a subset of the patch-based AMR. These are two. The upper right is the initial conditions for a merging white dwarf calculation. The lower left is something that Donna Calhoun has put there. And then again, these are the levels of refinement she sort of extracted out so that you can see them better. Okay, this isn't new. So I don't want you to think, oh, wow, adaptive mesh refinement has just come about. It goes back to the 1980s, an early paper, 80, actually I'm not quite, it's 346, somewhere in there, talking about how to do this for hyperbolic conservation laws. Hyperbolic conservation laws are really nice because you can write them in a flux form. So the update looks like a difference of fluxes. You can do an explicit update. You heard about explicit. It's very easy. The new value depends only on old values. So you don't have to do a matrix solve. And the way that you synchronize coarse and fine is very straightforward because you've written in terms of fluxes. If the fluxes are consistent, the method is conservative, life is good. Okay? So that was the early work, and then AMR has been extended. So AMR in the early days, if you said AMR, it meant AMR for hyperbolic conservation laws. AMR now is a much more general technique that we are using for all kinds of multiphysics operations. And one of the things about it is you've got to understand the physics, you've got to understand your discretization to do it right. So the software will do a lot of things for free. It doesn't do the math for you. It doesn't tell you what the right synchronization operation is. So in that sense, you have to think harder. To me, that's as it should be. Okay, I thought about trying to put a list of packages up here. There are many different frameworks out there. They're written in different languages. They have different histories. They have different levels of support. So some of the websites you go to, they haven't been updated since 19-something. There are different styles of refinement out there. There are different application targets. Again, hyperbolic conservation laws. There are packages specifically for elliptic solves. And then we have frameworks from complex multiphysics. The website that I like, Donna Calhoun, who's an associate professor up at Boise State, she keeps a website that's relatively up-to-date of packages. So this should be in your notes. You have this link. You can go there and poke around and see all the different packages. Okay, so AMRX is, so ECP is the exascale computing program. As you know, they're one of the sponsors of this event. There is a co-design center in ECP specifically for block-structured adaptive mesh refinement. So AMRX is the software product of that co-design center. It supports the development of block-structured AMR applications. And again, we're very architecture focused because this is about, the ECP is really focused about next generation. So we want it to work now. We want it to work better than anything else now. We want to work and work well in the future. AMRX was not designed from scratch. There were two packages at LBNL, BoxLab and Chombo that you've heard about. BoxLab is currently completely deprecated. We've replaced it with AMRX. And basically, features from Chambo are being migrated into AMRX. So in a couple of years, there should just be one. OK, it's freely available. You can go to GitHub. You guys have the link. And originally, Boxlight came about as, again, hyperbolic conservation laws. Then we did elliptic problems. Then we did incompressible Navier-Stokes. Then we did combustion. You'll see a bunch of applications. The takeaway from this bullet is that the fact that you're solving your equations with block-structured AMR doesn't tell you anything about what your equations are. It doesn't tell you anything about how you discretize it. Basically, it just says, here is a framework. Here's a structured grid framework. We're going to do a lot of things for you, and I'm going to tell you what those are. But you have to know what you want to do. I feel very strongly that the software should not dictate what you do. We've had cases where you say, well, I want to solve this. They say, well, no, you can only solve this. And my answer to that is, no, that's a problem with your software. So there are things that this can do, but it shouldn't be telling you, I'm sorry, you have to use a second order Laplacian. You have to do it this way. You should be deciding that based on the mathematical grounds and the physical grounds. The software should be there to support you. That's one of my, oh, hi, Laurie. That's my 5 minutes. OK, so just as I just thought Laurie was friendly. Hi, everybody. Combustion, astrophysics, cosmology, flash, accelerators. I know we have Maxence here from the accelerator project. Multi-phase flow, that's a particle fluid application. So there are a number of things that we can do with this. What does it do for you? OK, it gives you support. When I say support, it gives you data structures. It gives you iterators. It gives you synchronization operations, explicit operations, implicit operations, single level, multi-level, particle, particle, particle mesh. We have some inherent or some native geometric multigrid solvers. More about solvers in a minute. It gives you the hybrid parallelism. You have to write your loops in a way that is compatible with OpenMP, but it will handle, in some sense, the distribution to threads. The core functionality is written in C++. There's a lot of times we have kernels in Fortran 90. We actually also have a version of it that is entirely Fortran wrappers of C++ functionality. Basically, the reason that you want the core in C++ is because that's where the computer scientists work. The reason that we supply the Fortran interfaces is there are people who just aren't quite ready to have to read the C++ calling the Fortran, so we give them an entirely Fortran interface. It's got the I/O for both restart and plot files. It's got visualization, so that, again, you're not writing the parallel I/O. You're not having to write the format that you try to get the visit guys to support or having to fit into some other format. OK, so that is the where does it fit in the software stack. Everything that's between the upper dark line and the, I guess, middle dark line, that's what AMRX does. So it depends on the MPI. Down here, we've got MPI, OpenMP, the PGAS models, partition global address space. So we have things that happen down here that we take advantage of so the applications don't have to see them. The blue, again, it's the core operations. These are things that there is support for them in AMRX, but we also are very happy to call outside things. Then you get into things like asynchronous algorithms. There's asynchrony at multiple levels. That's a whole other conversation. Let's see, some of the different, you hear the phrase runtimes. There's essentially a runtime in this. And then up top are the applications. And I haven't told you what they're doing. They're doing whatever they're doing, but they have this support to leverage. The idea is that you don't have to go and write all of that from scratch. OK, what doesn't it do for you? It does certain things very well, but for example, AMRX doesn't have an algebraic multigrid solver. But AMRX will give you an interface to be able to call Hyper, for example, that you'll hear about, or PETSI. We don't have a specialized ODE solver, but we have an interface for calling ODE solvers. So the idea is it's not pretending to take over the world and do all of this for you, but it's supposed to give you a place that you can start and be able to access all of the other software packages that you're going to hear about today. OK, how do you use it? This gets much more complicated. If anybody is interested, talk to me later. There are 3 levels you can come in. One is you say, I just want to use the data structures. I've got a single level code. I don't feel like typing MPI. OK, the point of number 1 is you can get parallelism without ever typing MPI. That's the takeaway. Number 2 is the same thing, but now we're giving you support for multi-level. Number 3 is something where you want a subcycling and time algorithm. You kind of understand what you're getting into. We will drive the subcycling and time and give you stubs to hook into. So people can come into this in many ways. So what's the takeaway? So in the sales pitch for this particular package, it's a framework that you can use to build a massively parallel multiphysics application, block structured adaptive mesh. You specify your discretization, you specify your equations. Again, you never type MPI. A lot of what you would normally write yourself is taken care of, the domain decomposition, the logical tiling, that's for OpenMP. Things like filling Go cells, communication for that. Things like refluxing the operation. And again, the support for particles. So if you can define your problem and you can write down what the discretization is and what mathematically should happen at the interfaces, you can build it. I'm at 0. OK, now we're moving towards a few hands-on. The point of the hands-on is just to give you an idea of if you wanted to play with it and you go to GitHub and you do a git clone, what can you do? And the way we're going to do this is I'm going to talk and Mark's going to type.
So I'll draw. You're our tour guide, and I'll just try.
But you need to bring up these structured meshes. So this is, I noticed in the last one, some people were sort of following along and some people were typing. You can do it either way. So I think everybody's on Cooley. If you do exactly what it says to do, you should get exactly the things that I get. If you don't feel like typing or something's not working, then what you should see is actually on the screen.
And so I'll say I'm up here in the up at the top level hands-on. So you want to CD into AMRX, and the first one we're going to do is AMRX diffusion, right?
Right. So this was playing on the theme. So we talked about the diffusion equation. So Mark did a very simple 1D code, and it was 500 lines right there. And he had to worry about the input, the output, the specifying of things, and he had some way of writing out the answers. But the way that he wrote them out may not have worked in parallel. I'm guessing that was a serial code?
Yeah, it was serial. Yeah.
So what he did wasn't going to work in parallel. And oh, by the way, if he tried to break it into multiple grids, well, he didn't have support for that because he assumed it was one array. So that was going to be a pain. If Mark wanted to take that and turn it into what this solves, there's a lot of code he has to write. But if you look at it, so again, here's the explicit, solving the explicit diffusion equation, or explicitly solving the diffusion equation. Okay, should look very similar. This is what you as the designer need to know. You've got to provide this part. Now if we scroll down, so that is computing the fluxes, doing an explicit update. If you think about what the operation looks like in its totality, you have an old state, you compute fluxes, you update the solution. At some point now you have a new state. You've got to redefine, you've got to copy the new into the old. That's what the copy does. And again, now you've broken this into multiple domains, or multiple subdomains, multiple patches. You've got to communicate between them, because if you update cell 0,7 and that lives on one grid, but 0,8 lives on a different grid, it needs to see the new value. And so what you get, again, if Mark was writing this in his program, he'd now have to be doing a copy saying, okay, so this grid, I want you to go copy from that grid. Well, he'd have to tell it, well, which grid do I need to go copy from? And if he's doing it in parallel, well, now he has to know the grid that's to my right, what processor is that on? Or he's got to do all-to-alls everywhere. It's going to get very intensive. This is what this is kind of doing for you. OK, so if you want to know how to run it, you CD into AMRX diffusion. I've put an executable there. We decided that we didn't want to try and build these things in real time. OK, there's an inputs file there. What do you have to specify? How many time steps? N cell is the number of cells in each direction in the domain. Again, this one's a square problem. We made this really simple. Max grid size says, how big do you want individual patch to be? So here I've said 128. That means I'm going to have, in 2D, I'm going to have 4 128 squared grids in a 256 squared domain. Plot int tells me how often I want to write a plot file. And in this case, I've made it doubly periodic. Let's see if it works.
OK. So I'm just going to cut and paste this command line.
So we're running a bunch of steps. Again, it's a 256 squared. Yeah?
So you mentioned that the overall interface is written in C++ with some Fortran kernels, and that looked like a Fortran kernel for the fluxes.
Yes.
Can I also write can I write C kernels and use the interface, or do I need to write Fortran kernels?
No, so we just happen to like Fortran because Fortran actually compiles really well. So you can write C. The thing that you as a user have to do is you have to write it on a patch. So you can't assume when you get to the high end of your patch that you're at the domain boundary, for example. But yeah, you can absolutely do that. Basically, what you do is the code is going to give you an iterator. The iterator is going to, it's a owner computes rule. So when you're looping over that grid, you're on some process. And as long as you've written your C or Fortran or whatever in such a way that you don't assume you're covering the entire domain, that's fine. Yep.
So Ann, one question. It looks like inputs 2D on disk actually didn't have 256, 256.
Okay,
so you want me to rerun it with
actually, it'll do the same thing.
Okay.
Okay, right. So if we scale, let's just scroll down to the pictures. So what I did here is there are a bunch of tools. If you have AMR data and you write out a plot file and you say, well, but I liked his animated GIF. I want to do 1D slices across this. there's a tool that says slice across the data. And if you do that and you animate the GIF, and actually it was interesting, we talked about performance portability. The hardest thing about running on Cooley was the Git version and the GNU plot version. The code built just fine, but sometimes the simplest things in life. And then there's actually, so again, you've gotten all this for free. We're going to scroll down a little bit just in the interest of time. And if you decide to use Visit, has anybody in here successfully used Visit on Cooley? You guys done that yet? You have. Did it work okay? Yeah. Okay.
Probably changed the geometry, but otherwise, because it opens
I-
like way too large.
I was going to
Oh,
comment on that at the
okay.
end here. I've already actually updated that script.
Oh, okay. So the plot file format that comes out of AMRX, it's natively supported by Visit and by ParaView and by YT. So it's something that's out there in the community, and if you want to,
Sorry.
okay. So if you decide to visualize step 0 and step 10,000, that's basically what you'll see. I'm not sure if it's worth doing at this point. So let's say for a minute, let's just skip straight to the parallel. So now you want to run this in parallel, okay? We have 4 grids, so we know we can run it on up to 4 processes. It turns out that users often forget to update their max grid size. So we've actually put in an option that says, you know what, if you asked for 16 processes and you only have 4 grids, we're going to make the grids smaller for you so that we can distribute them to processes. Because we've had that happen too many times. But here again, if you do the MPI, okay, is that the first one?
Yeah, there's the 4. I did the 4th one. Did
Okay.
you want
So
me to
yes, I
start
want
that
to
one?
see the, so what we're doing here is the code is built with MPI enabled, which means if you run it with MPI run, is it run or exec here? Well, MPI exec -N1 -N2 N4, you can get that many processes, and you'll see, okay, so we've gone from 5 seconds to 8 seconds.
Well, so I'm sorry.
Oh, go
I
ahead.
threw you off, Ann. The one run I just did was the just one processor run that Ann wanted me to do. That took 8 seconds, and now we'll do the. You want me to do the 2 processor
Well, the
run?
2 and the 4 was,
Okay.
yeah, if you.
So now we're going to do the 2 processor run.
And the runtime is just something that's a timer that we've put in to make it easy to take a look at this. So 1 processor was about 8 seconds, 2 processes was about 5.7.
And now we'll do the 4 processor
And now we'll do the
run.
4 processes. And one of the things you'll notice, by the way, is it's not perfect scaling. So I think you guys have had all kinds of discussions about MPI and OpenMP. You'd really like to see that be 842. Basically, one of the things that you will learn about is that is a very idealized model. It works when there's a lot of computation per core. In 2D problems, it's hard to get that. So what we're seeing here, it is improving as you use numbers of cores. It's not a great case for a scaling study because you're not doing as much work. What you're seeing is the communication. Okay, so that's just a statement about the reality of these things. Again, we wrote plot files. We did an extract to get 1D. We had a script that did an animated GIF if you want to look at the 1D. So that's the diffusion example. Yeah.
For the Unigrid version, how
Yes.
well does it scale? Or so how much is the overhead from AMRX in total if you just want to use the Unigrid?
So you're not seeing overhead from AMRX in particular? I mean, so you're talking about running 1 grid, 1 processor, and just making it bigger?
Yeah, just basically. Yeah.
Yeah, I mean, the work is in your loops. It's in your IJ loops. So yeah, you should see very good scaling there. When you get to multiple cores and especially multiple nodes, you start to see a lot of effect of the connectivity and how the machine is laid out. But yeah, you don't, with a single grid, you might be, if you're periodic, you're copying data over here, but it's all local copies. So you're really not seeing anything. It should run the same speed as you can run if you hand-coded it. We haven't done anything special to lay out the loops or to, there are things that you could do to make it vectorize better. We haven't done any of those special things.
From grid
Yeah.
on MPI with a lot of nodes, like because the overall.
Right. It's basically as good as something you could handwrite. It is optimized beneath the surface. Yeah, there's a lot of work that's gone into, we compute who the neighbors of the grids are, we cache that information, you're not recomputing it. So basically as good as you could do if you hand-coded it. Okay, second example, just to give you an idea. And
Okay, let me interrupt you just once.
Yeah.
So we're going to CD out of this directory AMRX diffusion, and we're going to go up 1 level, and now down to AMRX advection.
And these examples are taken from the tutorials. If you go into the AMRX directory, there's a tutorial subdirectory. There's basic AMR particles and hyper there. If you go into basic, you'll find the diffusion example. If you go into AMR, you'll find the advection example. And here again, we're doing a flux-based update. This happens to be an advection problem. So these are advective fluxes. I didn't write out what they look like. And basically, here we have a time-stepping loop that operates over levels. So this lower gray box right here, this is basically what it looks like to subcycle in a single physics case. And what you can see is we take a time step at level 0. If we have a finer level, we now take 2 time steps at level 2. We come back and we reflux. Reflux here means we replace the fluxes at level 0 with the average of fluxes at level 1, and we update the solution at level 0 that used those fluxes. And then we do an average down where we say the solution at level 1 was a better solution. I'm going to average that down where I can. So if you want to run this problem again, there's an AMR advection. Again, the same style. We tend to operate with an inputs file. You can have other files that it reads. And again, we have max step. We have end cell, max grid size, plot int. And, oh, I didn't. OK, this is a single level case. I run with AMR.max level equals 0. And you can see if you scroll down just a little bit. So that's what you're going to see. This is actually, you just have a patch of a scalar. We have a vortical field, so we're moving the scalar, and then actually you run it back. It's a time-dependent field, so it rolls out and then it rolls back. So you can do an error analysis by testing the initial and the final condition. This is something that you can run there. Again, with visit, you can either view them statically or animate them.
What if we went up to level equals 1 here?
And now, so now the obvious thing is, OK, let me make this higher level. Let's run with level equals 1. Let's see what happens here.
Okay.
Okay, so there's a bunch of print statements. Again, you advance at level 0. Level 1 is a factor of 2 finer. You take 2 substeps. Oh. It doesn't have print statements for the reflux or for the average down. And now if you look at these, so let's look at our.
Sorry.
So now you see there's 2 levels of grids. The largest, let's see if I. So if you can see these black lines, whoa, didn't want to do that.
Let's try clicking on that.
Okay, so these black lines here are the 4 level 0 grids. The white lines are showing you the level 1 grids. Again, it's broken into 4 because I had a max grid size. And these finer black grids, which are hard to see, unfortunately, those are the level 2 grids. And if you look at this, you can presumably see that, well, let's see, I go too far here? Whoop. OK, I went way too far here. So that's looking relatively coarse, but now I have the same domain. I put refinement. Now, what are the things I haven't told you? So the obvious thing is somebody had to decide where to put the grids, okay? And there are different ways of thinking about that. And again, in some sense, it's hidden. I didn't put it here, but it's in the code if you choose to read the code. You have to have some reason to refine. We call that the tagging criteria. So in this case, I said, you know what, all I care about is the phi. I don't care about, I might have a vortex in the corner. I don't care about that. I only care about the scalar. I'm going to refine where the scalar is greater than, I think it may be greater than 0. It's actually kind of interesting. If you look, there's a little white box on the bottom right. And I kept thinking, well, what the heck is that box? Is it broken? And what I realized is that's actually the tail of this thing. I think I'm refining on where phi is greater than 0, and there's just a little bit, and this is a periodic problem. But you could decide. So if you run the flash code, for example, there's a default that says, basically, wherever the scaled Laplacian of a field is greater than some threshold, that's where I want to refine because I know that things are changing. Right? Sometimes you have a gradient. You want to refine where there's a gradient. But a gradient can be very smooth, so maybe you don't want to refine there. A Laplacian's a good metric. A lot of times, again, in multiphysics, I've got a whole lot of variables. And if I pick up the Laplacian of every single one, I'm going to be refining the whole domain. So I might know vorticity is the big thing. If I'm doing a combustion calculation, I might have certain key species that I know are marking the region I care about. So you as the user have to, again, you have to think about where do you want to refine. There's an interface set up for setting this up. You say, OK, I want to refine where phi is greater than 0.1. Those values are very easy to specify. But you have to make that decision.
I was just bringing up the actual live viz there.
Yeah, so Visit, again, Visit supports this. And you can see the grids. And you can animate and all the things that you can do with Visit with the other formats. So I'm going to stop here and just say if you do feel like looking at it, there's, if you download it from GitHub, you go into docs. There's a user guide there. I think it's up to over 100 pages. But it is laid out in chapters, so you can find what you want. The tutorials are there if you feel like playing with it. And in the last minute and a half, are there any questions?
Some folks are having multiple applications.
So how are you dealing with the increased complexity? So I'm assuming like you have to have communications now of all those.
Yep.
So are you putting them like more on one node to reduce the communication, or spreading them out to increase parallelism?
Okay, so that is actually one of the key questions. So load balancing strategies, and the answer is there isn't a single answer to that. So we have multiple load balancing strategies that are supported. So so in load balancing strategies, you want to average the work out across the domain, and you also want to minimize the communication. At a single level, they're relatively straightforward strategies like space filling curve. At multiple levels, the question is, do you want to prioritize locality at each level, or do you want to take into account locality relative to where your coarse grid parent is? The other thing that happens is you have heterogeneous workloads. What is the best load balancing for one operation is not necessarily the best for the other. So sometimes with particles, for example, we lay out the mesh data differently than we lay out the particle data. So if we have a small region that has a lot of particles, we'll distribute that differently. So there's a lot of complexity. There are a number of defaults available. They may or may not be optimal. And that ends up being relatively application dependent. You profile and you figure out what is the strategy, where is your work being going. Even with a single set of like equations and application, you might have very different regimes, and you might use different strategies for those. Okay. But yeah, it's a hard problem, and one of very active interest in research. I'm done. Thank you.